So the learning outcomes for today's session that I hope you will get out of it. Bradley, I will share the presentation also afterwards. I hope you will be able to see my screen within the next few minutes, but I will share it in any case as well. So the learning outcomes is firstly to understand what is a voltage dip, who or what causes voltage dips, to understand how voltage dips are measured using power quality analyzers or dip recorders, to be able to configure a power quality analyzer to record voltage dip, and this will specifically focus on CT Labs platform and CT Labs software and hardware with the focus on that. And then lastly, to understand the importance of a voltage dip management system or a platform that you use in your network. Okay. So quality of supply, there's a few parameters that qualifies for quality of supply. We've covered that in the previous session, and that the NRS 048 Part 2 with the latest version 2015 defining limits or compatibility limits for some of these values or some of these parameters. Today we'll focus specifically on voltage disturbances, mostly looking at voltage dips, and then also just briefly looking at swells and voltage transients. Okay, so introduction. Voltage dips are probably the most common power quality phenomena that you'll get in your system. That could be a range of power quality dips, some more severe than other. More than 90% of these dips are due to network faults, short circuit faults, single phase to ground, line to line, or three-phase faults. And of those 90% of them are normally single phase to earth faults. Now, in order to manage waveforms or your quality of supply and the events that happen, such as voltage dips, you need to know what is the root cause of such an event. And to be able to analyze that and determine what is the root cause of a voltage dip, you need to record data. You need to have some way of characterizing that voltage dip in a way that you can analyze that to get to a root cause. And you will normally want to have data for a period before, during, and after the event to be able to see how the event started, propagated during the fault, and how it was cleared or recovered in the end of such an event. Okay, so who is causing voltage dips? Now, both the utility as well as the customer or user both can contribute to voltage dips in your network. For example, fault currents can originate from anywhere in a supply system, and some examples of causes of voltage dips are, for example, bird streamers. It could also be bird nests or birds that just that's flying in the wires or in an overhead line. It could be fire, and from the fire it causes pollution or the particles in the air that can cause a flashover in an overhead line. It could also cause maybe the pole to burn down or fall over. You get lightning events. That's more common northern side of South Africa, not that common in Western Cape, where I am. And then tree contacts, animals such as, again, birds, squirrels that climb on a transformer, rats, snakes, all of that. Pollution is one cause as well. Cable faults, cable theft, etc. That's a few causes, and most of these are out of the hands or not. Most utilities or municipalities will not be able to really look at that or determine that. That's not normally out of your hands. But there's also a few things that can be caused by, or a few dips that can be caused by normal operation, such as the energization of loads downstream caused by voltage dips. Now, this is mostly three-phase and balance. That can be because of direct online start of an induction motor, or even switching and transformer energization can lead to current inrush events. And this is something that we see more often because of load shedding the last few years. Okay, just a few images. Here you can see a bird with a bird streamer. You can see the effect that it has and can have in an overhead line. Here's an example of a few bird nests. And you can imagine if that gets quite... You also get buildup of feces of bird. You get buildup, and that can also cause damaged insulators, lead to faults, and so on. Then here's an image of lightning striking electrical network that will cause a dip, cable fault, and then example of a wildlife, a squirrel that climbed on top of a transformer, and you can see how it burned and the damage it caused, and also unfortunately to the animal as well. Okay, so what is a voltage dip and a swell? A voltage dip is a momentary, between 20 milliseconds and 3 seconds, decrease in the RMS voltage on one of the phases or more phases by more than 10% relative to a reference voltage. A voltage swell is the same, but it's a momentary increase in the RMS by more than 10%. This 10% is what's declared in the NRS 048 as a dip. So 10% below and above a reference voltage is seen as, then it's seen as a dip or a swell. Now, if a dip or a swell is longer than 3 seconds, now for a dip, it's then classified either as an under voltage or an interruption depending on the depth of the dip. And for a swell that lasts longer than 3 seconds, it's then classified as over voltage. Voltage dip are more frequent than interruptions. Some interruptions that can happen is because of maintenance, plant outages. There could be some switching that was done for a minute or a few seconds that lead to an interruption. There's a few examples, obviously load shedding. Now, it's not always, as I said earlier, most of these root causes are not under the control of the utility. And for each network, this will be unique. So wherever you are in South Africa or in the world, your characteristic of your network, how it looks, external factors will all play a part in the voltage dips and the characteristics of your network where you are. So how is a voltage dip or event triggered? A detection of a dip or a swell or an interruption is based on the half cycle or 10 millisecond voltage RMS values. So a power quality instrument such as the VECTO 3 that CityLab provide or manufacture continuously track the RMS voltage in a half cycle resolution. Now, this is the minimum standard from the IEC 61000-4-30. This can be better. So, and this is also the specification for a Class A device. The moment you have a Class S device, then this becomes 1 cycle or even more. So this is just specifically for a Class A standard or device. Now the VECTO 3 tracks this using 1/6 of a cycle resolution and not just half of a cycle. So you get more samples per cycle, per phase to analyze and to look at the RMS voltage dips. This also leads to generally a more accurate characterization of how a voltage event looks and the duration of that. Okay, so a voltage dip is characterized and the minimum, while the minimum information that's required is the residual voltage or the depth of a dip and the duration. Now the residual voltage is the lowest 1/6 cycle RMS voltage value during the dip in any phase. So if you look at this, the residual voltage will be the lowest voltage in any one of the 3 phases. And the depth is the difference of the depth is the difference between the reference voltage and the residual voltage. So this will give you, for example, if you have a 60% residual voltage event, then that's a 40% depth if the reference is the 100% nominal voltage. Okay, the duration is determined when the first phase drops below that dip threshold. So in this case, the red phase dropped below the threshold. That starts the event, and the moment when all three phases recovers or restores above the dip threshold, plus, very importantly, a hysteresis value. We'll discuss this a bit later as well. Then the dip is ended. And the difference between the time difference between these two is then the duration of a dip. And it's the same for a swell. It's then just an increase in your RMS voltages. Okay. Okay, now the Vector 3 can be configured to obtain additional information. So more than just the standard RMS values and the depth and duration. And it also can be set up to include pre and post data. I will show you a slide that explains that a bit better as well. So what the Vector 3 does is when an event is triggered, basically a user configure what additional data they want to record for an event. So you can enable voltage and current waveform data for before, during, after event. Then it's the standard 1/6 cycle RMS profiles of the voltage, current, active power, reactive power. And then you also have 200 millisecond RMS profiles and 200 millisecond harmonic profiles. All of these are additional ways to characterize an event, and this data can then be used to analyze and to determine the root cause of the dip. Now, the extent of these parameters, so you're selecting this, and the window can be configured. So you can configure what must the window of data that you want to see during an event. Again, I'll show that in a nice image in one of the next slides. And this will, then you'll be able to use this data for extensive analysis to reveal the character of the network. A characteristic performance of a network is normally revealed over time. So you take into account design, climatic factors, maintenance, loading. All of this will impact your characteristic performance of your electric network. And normally that, to get a benchmark of how your network looks in terms of the performance, you need to look over a longer period of time to get a benchmark. And obviously the events can have serious impact on users and customers. We'll also look into that. Okay, so how to configure voltage dip and swell monitor. Now this is specifically using CT Labs software or cloud-based platform. For those of you that don't know yet, we call this platform Osprey Pro, and we're actually transitioning over to VECTO Grid OS. So it was formerly known as Osprey Pro. On the right side of the screen, I have a screenshot of the monitor that you can set up on the device to trigger for a 3-phase voltage dip and swell. Now, just some background, the software, there's a lot more monitors that can be enabled. So this is just one example. So this is for 3-phase voltage dip and swell. You can also enable voltage spike, voltage transient, current exceedances. There's more other monitors that you can also enable to trigger for waveform recording. And for all of them, you will be able to capture detailed analytic data that you can use to analyze the cause of whatever caused that event. Now, just for the setup of a 3-phase voltage dip and swell that we're discussing today, there's a few important things that you need to understand to correctly set it up. Firstly is the lower limit and the upper limit. This is the value that is normally as a percentage of the declared voltage that is used as your reference voltage. But this can also be, you can also use a sliding reference voltage by enabling that tick box there. But that's not from the standards. It's optional. It's not required to do or to use a sliding reference. A sliding reference is calculated using a first order filter with a 1 minute time constant updated every 10 cycles. So it doesn't just use your declared as your reference, it updates using a value calculation to what actually your reference is. As I said earlier, that's optional. Okay, the next important thing is the hysteresis, as I mentioned earlier. What this does is when the event drops below a dip, there's a dip and it's below 90%, the event will only be stopped or the dip cleared in the system, the monitor, when all three phases in the RMS voltage goes above your upper limit of your limit, your threshold, the 90%, plus your hysteresis. So you add this on top of the lower limit. In this case, it's 0.5. Now, in the standard, they mentioned that typically the hysteresis is 2%. So you can increase that if you want to. All right. So that now, what does this? Why is the importance of this? Basically, if you have a dip that's just below 90%, so it's not a very deep dip. What can happen in the middle of an event is that the phases restores above 90, just above 90. And then drops below it again. If you don't set this hysteresis value big enough, or if you don't set anything here, then that could lead to multiple dips being triggered for actually the same cause. And you don't want that. You want to capture, you want to see it as one dip because it's the same one cause that there's one thing causing the event. So you set a hysteresis value to make sure that doesn't happen. Okay, then the hold off period. This is just a period where the dip, it needs to go below the lower limit for longer than this period that you set here before it's classified as a three-phase voltage dip and swell. In this case, as from the standard, that's 20 milliseconds. So when it's longer than 20 milliseconds, then it's classified as a voltage dip or swell. Otherwise, it's either a spike or a voltage transient. Okay, now this, as I said earlier, a number of data or data streams that can be recorded for additional data during an event. You have the voltage and current waveforms. You get the 6-cycle RMS values and phasors. So it's not just the magnitude, but the phasors as well, or angles. Then the 200 milliseconds and 200 millisecond block harmonics. These are all, you can also enable for additional information. And just some background as well, on Osprey Pro, we have a function where you can actually plot the FFT of a waveform. So you'll be able to get an accurate representation of your harmonic spectrum as well during an event. So you can do that as well.
What is FFT?
Fast Fourier transform. So it basically characterizes your voltage waveform, then in a frequency spectrum per individual harmonic, so 50 Hertz, 100 Hertz, 150 Hertz, of what that component is superimposed on the fundamental voltage and current, if that makes sense. Okay, so these periods can be changed. This is just the default. You can change these. Each one of these periods or durations can be changed to 2 seconds max each. And I will show on the next slide, I will explain the difference between the different periods as well, so that you understand that also. You just basically configure the window size that you want to capture data for during an event. It will make sense in the next slide.
Sorry, just on this note, maybe it's good to mention that this 2 seconds is not really a major limitation, because you could activate waveform data on 3 seconds if you're investigating something longer.
Yes, you can actually do a triggered snapshot as well, where you can take longer waveform recordings if you want to do that as well.
But in the electrical world, 2 seconds is a lifetime if you consider a cycle is 20 milliseconds, yes.
Yes. Okay, and then the last things that you can set up for each monitor, this is not just unique to three-phase voltage dip and swell, is also relay settings. So the Vector 3 has 4 relays, where 3 you can use for to trigger when there's, for example, a dip. So you can specify a relay, let's say relay number 2, to close that relay when a voltage dip is triggered. And you can also change the way that that relay operates using this auto reset function. What this does is if you tick the auto reset, if the dip is triggered, the moment when the dip is restored or when the dip ends, that relay then opens automatically. If you don't tick this auto reset, your relay will function almost like a counter. Every time there's an event, the relay will either close or open. So you can, for example, connect this to some external SCADA system, or so that you can use to either determine the length of a dip, or you can counter the number of dips as well. But again, if you're using VECTO Grid OS or Osprey Pro, you will have all of that information in any case in a lot more detail as well. Okay, so to explain the different durations, as you can see in the previous presentation, there's 4 durations that you can set up. It's the start pre-duration, start post-duration, stop pre-duration, and then stop post-duration. Now, the difference is the start pre-duration is the period before the event started. So going back to the previous image we had, this is when the event starts, or the event was triggered, the moment when the first phase dropped below the dip threshold. Okay. The start pre-duration is the period before that you also want to save the diagnostic data. So that's the waveform data, RMS, harmonics, and so on. The start post-duration is then the period after the event started. So here the event started, and the period after that. So while the event is happening, during the event that you want to capture. And the same for a stop pre-duration. So on this point, the event is stopped or closed. That's when all 3 phases restored above the dip threshold plus the hysteresis. The hysteresis is not indicated on the image, but plus the hysteresis value. And this stop pre-duration is the period before the stop of the event that you also want to capture. So it's again part of during the event. And then there's the stop post-duration, which is the period after the event was stopped that you also want to see. So what you can see from...
Maybe on this, just a real example for the guys. The gap between the start post-duration and the stop pre-duration, there's no real limit to that. Real-world application would be something like load shedding. If your device is on backup power, external battery power, your battery tripping unit for so, and you set a start pre-duration of, say, 2 seconds, start post-duration 2 seconds, the gap between the start post-duration and the stop pre-duration, there where Heinz text says RMS in the middle, that can be any amount of length. So that can be, say, 2 hours if it's an outage. Then the stop pre-duration catches the waveform RMS going back up again. So that's one thing that this graph maybe doesn't indicate correctly.
Yeah, and again, what's important for you as someone that's analyzing an event or a dip is what happens, what's the change from your stable to let's say a stable condition during the event. Now there can be some changes during a fault, but normally you want to see how the event started and how it restored. You're not that interested in what's happening in the middle per se. You have all the information that you already need here and on the end. Now, if this period plus that period is longer than what the actual duration is, so there's no gap here in the middle then you're just capturing all the information. You then have the whole window. So this is just when this event is longer than a certain period. For example, the event is 1 second long. but this start post duration is only 20 milliseconds, and that's also only 20 milliseconds. Then there's a big period in between where you're not storing data. Okay. Okay, so how is a voltage dip characterized from the NRS, according to the NRS? Again, they're using the minimum data, and that's the depth and the duration, to specify what sort of event, what type of event it is. So it's dependent on the duration and then the depth. So here you can see the Y dips, which is the most common events that you can expect. Then X1, X2 is shorter events, but quite deep. Then there's the events in the middle, S-type, Z1, then it's a longer event. Z1 longer, but not that deep. Z2 long and very deep. And then T not as long as the Z2, but also very deep. Now, anything below this or longer than 3 seconds then becomes an interruption. Or the moment it goes, it drops to 0, and it's for longer than 3 seconds, it's either under voltage or an interruption. So what you'll see is a scatter plot. Normally there's a scatter plot that you use to plot the depth and the duration of an event. And that will classify then what type of event it is. Now, most equipment is designed to withstand Y dips. And dependent on the sort of equipment you have, it could be VSDs, electronics, laptops, computers, or whatever, will determine how sensitive it is to different events. So normally, the deeper and the longer the event, the more sensitive or the bigger the impact will be on your equipment, and it can lead to trips, VSDs that trip, and so on. Now, this scatter plot is all in reference to what your reference voltage is that you set up, which is normally your declared voltage. As I said earlier, you can also use the sliding reference, but the default is the declared voltage. So let's, for example, take you on MV on 11 kV, and you set a declared voltage of 11,000. Then everything will be in reference to that 11,000 value, but it will be as a percentage of it. So what this does is now you can actually compare data or events on different locations or different points in your network, even on different voltage levels, because it's all as a percentage of the declared on that voltage level. And you can see how an event propagated through your network. So yeah, if you've installed power quality instruments on various voltage levels, and there's a big network or utility ESCOM fault, for example, you'll be able to see how that propagated through your network and impacted on your customer or LV side of a network. And then that's why this scatter plot becomes important over time, to be able to compare events on different places, different points in your network, and also to get a good understanding of your characteristic performance of your network, what sort of events you normally get, and also you'll normally see patterns. It could also be seasonal. So certain times of the year, for example, here in the Western Cape, we expect more rain and so on in the winter periods, but then in the summer, we get more wind. All of that can play seasonal effects or factors on how the networks are performing during that period. And if you measure over a long period, you can benchmark that quite accurately. Okay, so the distance to the fault versus the dip depth. So the distance to the fault determines the depth of the event or residual voltage. The closer you are to a fault, the deeper the dip, and that's just Ohm's law. So the impedance is less. So the product of the fault current and the impedance results in less voltage. Now, the duration of a dip is normally determined by the type or the setting of your protection or your overcurrent protection. So on HV or extra high voltage protection normally clears faster than on MV and LV overcurrent protection. So over time, if you characterize your network, you'll also be able to determine if that event is from HV or where it propagates from, or is it maybe MV or LV, just by looking at the duration and normally the depth of an event. So dips at higher voltage is normally shorter than at lower voltage, just to conclude on the above. And just important also, your network configuration also contribute to the depth. So that's why it's difficult to compare different electrical networks with each other, because the configuration and the characterization of that network will be different on different places or in different networks in South Africa. Okay, so here's an example of the scatter plot from the NRS. Again, there's your dip categories. When it's longer than 3 seconds, it becomes either an under voltage or interruption. And then the same for it's a swell below 3 seconds and an over voltage if it's longer than 3 seconds. So this is all reference to your 100% declared value. Okay, this is for a specific client, a specific site. I'm not going to mention the name, but this was data captured over a 4-month period. Voltage dips and swell. You can see the events plotted on the scatter plot. You can see there was 49 Y dips, 5 X1 dips, 1 Z1, and so on. So you'll be able to get a good percentage of the number of events. As I said earlier, Y dips is the most common. There's also 12 voltage swells. Now, the important thing here for this client was that 12 of these events or incidents actually cause trips and production stoppages. Now, that could be your electronics issues, it could be VSDs that trip, and all that can lead to either production losses, product damage, or even sometimes that loss in production cannot be gained back. So it's permanently lost. If you manufacture 24 hours and you have a loss in production because of a dip for a few hours, you can't make that back up. Okay, and that's why it's important to do root cause analysis, to have enough information to determine what events on this scatter plot at what time caused certain equipment to trip or be impacted. And if you start to understand what impacts your plant, you can maybe mitigate that, or you can even assign ownership to whoever is causing this event. So it could most likely the utility, and you can start to analyze and investigate what's causing these dips and how is it impacting your plant. And you can actually add a cost to that, which will then you can then use as an ownership and as a responsibility for that event. So that's why it's important to analyze this and to have a good voltage dip management system in place. So as I said earlier, voltage dip performance of one customer may not be as bad as for another. The performance can be measured against economic consequences. So this is sensitivity of a customer's processes, equipment, and then the financial loss because of that sensitivity. So it becomes important to benchmark to determine if the dip performance is poor. Now, benchmarking against characteristic numbers of dips in that network. So you need to benchmark on to get a characteristic number of dips in that network. Or you can compare that with the NRS 048 characteristic dip numbers. But this is derived normally from Eskom data. So it's a national perspective. And as I said earlier, you can't always compare your network, let's say, for example, a municipality compared to the whole of Eskom, because the dip performance will look different. Your perspective is a lot smaller, and your characteristic dip performance will be different. So it's better to get a benchmark on how your network is performing over time. So for example, you measure for a year, you get a good idea of the dips to expect, and you start to benchmark year per year if the dip performance decreased or if it actually increased. If the dip performance is decreasing and you have enough data to then bring to the utility and tell them that the dip performance is decreasing because of dips from the network, then there's ownership to that. There's responsibility. They need to do something about that. If they can, obviously. So this is just the two tables that I screenshot from the NRS 048. There's two tables that's just defining basically the characteristic values for different sort of type of dips on different whatever category you fall in. So you on extra high voltage, so what your voltage level are, and you can then compare your benchmark to these individual values to start off with, just to get an idea if it's high or lower than the national benchmark. Okay, so just to talk a bit about voltage dip management, dip data must be recorded over a long period for statistical significance based on good data availability. Very important to, if you have power quality analyzers installed, to ensure that your data availability is high. And that's just to make sure that you have an accurate representation of your network over time. If there's big gaps of data, periods or months, then it becomes less accurate. So in a full year, you include seasonal factors, and several years will obviously help you to get a useful characteristic dip performance of that network. Okay, I mentioned that already. Then after time, you can assign responsibility. So a site performs poor against a benchmark, then the utility mitigate, or if a site performs well against a benchmark, but the dips are business risk for clients, so there's process losses or risk to a client, then it becomes the responsibility normally of a client to mitigate or to ensure that their equipment is not that sensitive or impacted by the dips. Okay, how can dips be managed? Client can install mitigation equipment, for example, active voltage conditioning devices. Utility and client can change the network or equipment operation, for example, how a motor is started, transformer energization, using fast reactive power support, or even upgrade the fault level or equipment such as transformers or cables or lines and so on. Okay, so just to briefly touch voltage transients and surges. A voltage spike or surge is a rise in the voltage above a threshold for less than 20 milliseconds. So this is voltage events that happen that's shorter than 20 milliseconds, and there's a different monitor that you can set up on Osprey Pro or VECTO Grid OS to specifically trigger for voltage transient and surges. Normally the default is 150% of the nominal or declared voltage, the reference voltage. So when the voltage spikes above 150%, using the instantaneous voltage data, instantaneous voltage, it's then actually seen as a spike. Again, there's extra configuration required. You can set up different what data you want to record, waveform data, harmonics, and so on. This is not a power quality parameter, so it's not, there's no assessed or it's not reported by the NRS 048. So this is handled on a case-to-case basis, and it's important if a user has a concern on installation strength of equipment. So equipment is designed to normally withstand a certain voltage stress, only up to a certain level. So it becomes important when you suspect there's transients or surges that impacts your equipment and you want to start investigating that on a case-to-case basis. So it's not something that you normally or necessarily need to monitor permanently, such as voltage dips and swells, because you don't need to report on it to the NRS 048. Okay, some things that can cause surges and transients is switching of capacitor banks, and so on. Okay, here's just an example of how a transient or surge looks. You have your voltage waveform, and then there's spikes, and that spike goes above a certain threshold that you set, and then it's triggered for waveform recording. So again, there will be a period before and a period after that you capture to see how it, for example, something that we've seen in some of our customers is the ability to identify cable failures that's going to happen or busy happening. You get quick spikes or transients in the waveform, and if you set this up correctly, you can actually identify this before it becomes a permanent issue, which you won't trigger that with just a normal dip or swell. Okay, so to conclude, before I do just a quick demonstration of Osprey Pro, is that a voltage dip management requires careful consideration of power quality instrument placement to provide visibility of the network. So you need to consider in your network where it's important to install power quality analyzers or dip recorders. If I look at the point of view from a municipality, you definitely want to investigate on the incomers, maybe your load centers, to be able to pick up voltage currents, fault currents in your network. As a client, you also want to measure your incomer, but you also most likely have certain equipment that may be sensitive to events, and to analyze that, you may want to consider also installing power quality instruments in locations where you have certain sensitive equipment in your plant. Something, for example, overhead lines, to analyze dips on that, you can consider on installing a power quality analyzer there to be able to trigger or see if there was a voltage event or any short circuit on that overhead line. Okay, voltage dip management take consistent and diligent event annotation and dip and trip matching over a period of time. So this is what I want to demonstrate to you, is the platform that was developed by CT Lab called Osprey Pro, or in the near future going forward VECTO Grid OS, that you can use as a management platform to consistently look and annotate events. All of that data is captured in the cloud, it's saved, and you can use that then. We have all the tools and functionality available with dashboards to then actually analyze your network dip performance. So voltage dip management also requires a person that's responsible for that. So that will be the power quality engineer, or someone that takes ownership of a platform. So you need to have a tool. That's normally what we say. You need to have an instrument, something that brings the data visible for you. You need to have, with that, you need to have a strategy, a dip management platform that you can use, and you need a person with the necessary skills and knowledge to do this properly. So yeah, to conclude, I hope this was an interesting presentation. You learned something from it. Before we take questions, or let's take a few questions you have on the presentation, then I'll move over to the demonstration.
Yeah, thanks, Hein. The first question that came up was in the chat window. I don't know if you want to speak a bit to what Tiro Yaone Matebele said there. I briefly addressed it, but perhaps if you want to dive a bit deeper in there.
Okay, can you just maybe, what's the question? Morning all, isn't the dips threshold supposed to be plus minus 10% according to the NRS 048? May you also please address how to set those thresholds to appear on the graphs on Osprey Lite? Okay, let me go back to the slide that was covering that. I think there may be some confusion. So let's first look at this graph. This dip threshold, this is for a dip, obviously. For a swell, it will be on the top. This is 10%, definitely. On our system, how you actually set that up, let me just go to that slide, is using the declared voltage. So the 10% that you're mentioning is the depth from the NRS. So it's a depth, 10% from your reference. How we set it up on Osprey Pro or on Osprey Lite is using the declared voltage. So from the definitions, again, the declared is actually the lowest voltage. So actually this is 10%. 10% below the reference and 10% above the reference. I hope that answers that question. And then the next part, may you also please address how to set those thresholds to appear on the graph on Osprey Lite 2. You cannot, unfortunately, from my knowledge, set that up on Osprey Lite on a graph, on trends. On the reporting, from what I understand, you will get a scatter plot that will show you a graph like this that shows you where a specific event is compared to that thresholds. On Osprey Pro, however, we do have a function to plot a trend that you can actually specify a limit. And I will show that to you also just on the demonstration so that you have an idea of how to do that, or if you're interested. I hope that answers your question.
I see a hand raised. Tiroyone.
Yes, good morning, Head. Yes, my question was arising from that 10%. If you go back to the previous slide, I think you call it hold off position. It was arising from that 20%. I'm not sure if it's 20 milliseconds, or is that one for? I thought you said that hold off position is your threshold.
This hold off is the duration or the period of how long a dip needs to be before it's classified as a voltage dip and swell. So it needs to drop below the threshold, which is 90% or a 10% dip, for longer than 20 milliseconds, or the period that you set here, before it's then classified as a dip. So the default is 20 milliseconds.
Okay, no, I get that. Just one extra question. Is it possible to also be able to show or to see a fault current during the dip or during opening and closing of a breaker if one wants to investigate, just for investigation purposes?
Yes, it's part of the waveforms that are captured. You're monitoring voltage, but Hein will show in his demonstration now, although your trigger is set to voltage, it also records the current waveforms, and I believe the power as well, Hein?
Yeah.
Yes, power, active and apparent and reactive, yes.
But I'm saying on the dip itself, is it as part of the, I think on the dip, you would probably able to see. I know on the trends, you'll be able to plot all the three graphs, either whichever graph you want to plot. But on the dip itself, you probably show the depth of a dip, and you show how long was it. Is it possible with the dip to also be able to see the fault current during that dip?
Yes, you will. As Randolph said, that is one of the things that's recorded as part of, so you have the RMS current that you'll be able to view. So just like you would be able to see the RMS voltage like this, you will also get a graph that will show you your RMS current during the same period of a dip, and the same for the voltage waveform and current waveform as well. So yes, you will be able to view the current. And just getting to your question on to see the current when a circuit breaker operates, you can actually use your circuit breaker status, connect that to a digital input on the VECTO 3 to trigger a recording when that circuit breaker operates or when it changes the state. And it will also then capture the current, or all of these information, all the waveform, voltage, current, and voltage and current RMS, waveforms and RMS, when that state then changes. And again, you can select this period that you want to record that data. So that's definitely possible.
Just before we head into Dani, Tiroyoane, I believe that a part of the issue you have is it not maybe being as accessible and visible on Osprey Lite. Like Hein alluded to, and his demonstration will also focus on Osprey Pro, or what we now call VECTO Grid OS. So there is more functionality in our web-based cloud monitoring platform that you might be losing out on at the moment if you only use Osprey Lite.
Yeah, for Osprey Lite, you'll need to go into the event to view the currents, where the voltage, RMS, and the duration and the depth is shown as default values. And you'll need to go into the event. So I don't have an example now in front of me, but you'll need to click on the event to analyze it further by plotting the trends for the current.
Perfect. Dani, into your question.
Yes, Han, can you just go to the general statistic or the general setup of DIPS, that slide?
Is it this slide you referring to?
Just I think the one before this one. Before. Just go back.
Okay.
I think the theory is in the front end. Maybe go forward.
Yeah, sorry.
Okay, before this is
where it says the cross-reference, which X1 dip, what defines the X1 dip, what defines the X2 dip.
Oh, okay. So this table.
Yeah.
Yes.
I was interested to see the column 2, the range of residential voltage. Why would that be so high?
A residual voltage has to do with the depth.
Yeah.
Why is that high?
Or why is that different?
Different compared to?
Depth as defined in 1, range for residential voltage.
No, it says residual. So what remains if you take your reference minus the range of dip depth? So 100% minus 10% gives you 90, 100 minus 15 gives you 85.
Yes.
So it's just another way of putting the same thing. Okay.
Exactly, yes. It's just another way of characterizing the voltage value during a dip.
Yeah, then just from working with RBM, they have the dip doctor there of spinning machine of 60 MVA just for the dip. That's another very interesting thing to know. So they spinning a 60 MVA generator basically to ride through all the dips on the mine.
So they're using that as a mitigation, almost like a UPS, rotary UPS.
That's basically a running UPS.
Yes, to basically provide reactive power support during a dip. Yes.
Okay. Thank
you. That's one way of mitigating also events here.
Sorry, then
capacitors, they have a big spinning reserve.
Okay, no, thank you for that, Donnie.
Thanks, Donnie. Brandon, your hand is raised.
Good morning, all. Hein, while we're on this slide, I see there's a note there on that dip characterization chart, where it says in the case of measurements on LV systems, it's acceptable to set the threshold at 0.85 per unit. That's what we are currently setting our thresholds for LV measurements, because in the past, when we were still using the vector graphs, we seem to have recorded a lot of dips that fall within that range of 85 and 90 of residual voltage. So it recorded a lot of white class dips, and it due to the space of that vector graphs, it overwrites the memory quicker. And then we were actually forced to set it to minus 15%, but we still kept to that in the Vecto 2s and 3s as well, where we install those instruments on LV. Then we set our thresholds to minus 15% because NRS does allow that. But do you perhaps know why on LV systems, we record so many of such embeds in the 85 to 90 residual voltage range?
Well, I think there's a few things that will impact the dip depth on LV. Firstly, it's obviously the loads that's connected to that LV transformer, for example. That will firstly impact just the normal reference voltage where it's running. And if there's more load, you can normally expect I'll say a deeper dip compared to an NV or HV. Also, you have voltage losses over the system, so your voltages may be a bit lower on LV, and all of that can lead to you easily or triggering a lot of wide dips in this area. That is more that you see more than that you would see on NV or HV level. And I think why this notice here, I wasn't part of the working group when this was set up. I am in this current moment, but is that most equipment on LV should be able to have immunity or withstand voltage dips also in this area, and not be that impacted as well. So that's just my comment on it.
Thank you.
Thanks. Herman.
Morning, Nine. The new name, is it a new name for Osprey Pro, this VECTO Grid OS, or is it a new program? Because usually in software, OS refers to operating system. If you can just explain a little bit more, please.
Yeah, Hein, do you want to give it a go? Should I attempt?
You're welcome, Randolph.
So the rebranding to VECTO Grid OS, you're 100% correct. OS stands for operating system. What we're envisioning with the brand change is to have a cloud-based grid operating system called VECTO Grid OS. Functionality identical to that of Osprey Pro. It's just a company-wide rebranding. You are all familiar with the vector graph, Vector 2, Vector 3. The range of devices now becomes VECTO. And we are slowly moving away from the word Osprey. So Osprey Pro equals VECTO Grid OS, and the idea is that it's a cloud-based grid operating system.
Okay,
yes, sorry, Aaron.
So for us at Eskom, that we're still struggling to get Osprey Pro going and doing it manually, some downloads, we will still use like Osprey Pro, or will we use?
So if it's local, non-cloud-based software, it'll probably be Osprey Lite. But whenever it connects to the internet or the intraweb, in your case, IT/OT integration, then that's a specific Eskom solution we'd chat to you about.
Okay, all right, so it's fine. Thank you very much. Can I ask another question?
Yes, please go ahead.
Okay, for the recorders, we know that we're all engineering people and we're full of nonsense when it comes to numbers, because there's a difference between 1001 millisecond and 1002 milliseconds. But if we take the recorders, and how accurate is the values that we see there? Because it's not just the recorder, it's about the CTs, and then Eskom, we use this class 2 CTs, and also the VTs, we don't use the protection VTs, we use the metering VTs, and then it's a cable and it's clip-on CTs and so forth. So what is a reasonable value that we can say, how accurate is the recordings that we see in percentage?
Sure, Hein, you dive into that one. On time accuracy, I can tell you, because it's GPS synchronized, we are 100 nanosecond accurate on time. But when it comes to the measurement circuits, Hein, do you want to dive in there?
Yes, I just wanted to make sure my mic is not muted. Yeah, there's, as you correctly mentioned, there's a few things that will impact the accuracy. But in terms of the Vector 3 specifically, that is a Class A device. We are obviously compliant to the highest degree of accuracy that's from the IEC. I just want to get that specific value for you. If I don't remember incorrectly, I think it's 0.2% or even 0.1% accurate on reading on reading the value. So the device itself is extremely accurate, up to 0.2, 0.1% accuracy that you get. But as you correctly mentioned, you have your VTs and your CTs that will add inaccuracy to the device. But normally that is more at higher frequency components where the VT and CT becomes non-linear. So on that topic, just for interest sake as well, so at 50 hertz, and that's what's used normally for RMS dips, will have the biggest impact on the depth of the dip. You can expect accurate readings, but the moment that you look at higher frequency spectrums, harmonics, you want to do analysis on that, even above THD, above the 50th harmonic, then the VTs and CTs will have a big impact on that accuracy because of the non-linearity that it brings on. And that's where we, in the moment, actually want to try and let's say introduce, or not introduce, but mention low power VTs or voltage sensors from whatever you want to call it, because the way that it functions is like a resistive divider. So there's no non-linearity in higher frequencies. You get a more accurate representation up to very high frequencies, broadband. So it's a broadband VT with a big bandwidth or high bandwidth up to very high frequencies. So the moment when you want to start investigating that, and you want to look at harmonic emissions specifically, even not even that high, at 1.5 kilohertz and up, then it becomes important to consider what VTs and CTs are being used that you're measuring on, because that will have an impact. Now, we've from CT Lab actually designed and manufacturing an amplifier. It's a low power amplifier, and you can install that in conjunction with the low power VT. The low power VT will normally give you a 1 to 3 volt output, so very small voltage output, but we can amplify that up to a standard 110 volt values that you will get from a normal VT. And that can then be plugged into the VECTO 3, and you can measure voltages as you would normally, just with a better bandwidth, and that's broadband.
So just on this note, yes. This note that Hein is touching now, the low power VTs are for a lot of cases cost and space effective. So if you have switchgear in a place where you don't have a chamber to fit a VT, a low power VT can be fit on the termination of the cable, and cost effective. It is quite cost competitive with the cost of an actual VT. If you then also consider the wider bandwidth of measurement, you will detect much higher harmonics than you could with a normal VT.
Yeah, and just Herman, also to add, the value that's specified in the IEC 61000-4-30 for the measurement uncertainty, so the error that you can expect on a voltage RMS reading, for a Class A device should be better than 0.2%. And we are even more accurate. I think if I remember correctly, we are as accurate as 0.1%, the VECTO 3. Now, the moment you start looking at using a Class S device, or a Class B, I think was also historically used, then the uncertainty becomes a lot bigger. Class S needs to be 1% accurate. So then you'll already get a 1%, uncertainty, or even higher for a Class B device. And that's why a Class A recorder becomes very important, to ensure that you have that high uncertainty in not just the value that you read, but also GPS time synchronization as well.
Okay, yeah, no, it's perfect. So what can we do, or let me ask it another way. Do you have any practical experience with values that you can say that due to the CTs and VTs and what and cabling that was used, the values is actually off by 2% on average or something like that? Because I agree, the instrument it got very nice specs, but I'm not too sure how accurate is the information we give to the instrument.
Yeah. We don't at this moment have a site where I can compare values. All is there's a big uncertainty of the inaccuracy that's being bring into because of VTs and CTs, but we specifically don't have a site at this moment where we have conventional VTs and then broadband VTs to compare. But we are in the future and going forward have a few pilot sites that we're looking at doing specifically this, and we want to maybe do a research, a bit of analysis to compare then the accuracy between the two. So if I have an answer for you, I will definitely share that with you in the near future, Herman.
Okay, thank you very much. Yeah, because you see this IPPs, they've got this proportionments, let's say harmonics,
Yes.
and it's very small values. So yeah.
So then it falls in the noise floor almost, and you then have no idea if that value is actually accurate. And it's not just the magnitude. For the IPPs where they need to prove compliance, the angle also becomes important. And that's also one thing that the angle can be shifted due to VTs and CTs. So definitely, I think there's some work to be done here, and yeah, just some info needed to be shared on this.
Okay, thank you for the feedback.
Thanks, Herman. Randolph, anything you want to add? I see you sent a few images.
Yeah, those are just snaps of our data sheet detailing the accuracy of measurement as well as the time clock accuracy. But yeah, Herman, like Hein said, once we have comparative data for you on sites that have both VTs and low power VTs, then we'll discuss it with the owner of the data, whether we could share that with you.
Thank you very much.
Okay,
just
thank you.
Sorry, Hein, I'm immediately thinking about the reason why this might be important specifically to them as well is like we all know, total harmonic distortion is capped to the 50th harmonic, and we do know that the bandwidth of a conventional VT it might filter out those high harmonics. So there are specific applications where you would be really interested in fitting a low power VT just to get the high harmonic apportionment.
Yes, it also can lead to resonances at specific frequencies. So then the voltage harmonics looks worse than it actually is, or it's introduced because of the resonance.
Hiro, your hand is raised.
Thanks very much, Rodolph. Just have two questions. Probably one related to these accuracy levels. Is when one tests the alarms systems to go out, say for instance, I've tried to simulate the trends on all the monitors we have on voltage regulation and balance and harmonics. Have you guys ever tested those alarms if they go through? Because one, if you were to take Omicron and inject the voltage, keep on dropping the voltage almost to 40%. Most of the instruments only respond up to 40%, but it's way below the lower bound of the voltage regulation. So I heard you talking about the deeps. Do you have any suggestion how one would test the deep threshold exceedance? Or
yeah, we in the office we have a Omicron test device. I think sorry, Tiroyane, it's most likely that what you're saying, alarms not going through, is that not an IT issue where it doesn't send the email in the right path, or are you concerned about a specific issue?
No, purely physically connecting, not even connecting via a network. Just testing with a multimeter on the outputs of the alarm outputs and injecting or dropping voltage from high voltage. Even on a 230 plug, you can just do your triggers and just keep on dropping or increase voltage, whichever test you want to test. But oftentimes in various instruments on the same vector trees, we get triggers of alarms at different levels altogether. So say, for instance, if you were to increase voltage over 110 and keep going, you'll probably almost reach 130, 40 before alarm can go through. At that time, yes, long time had an accident already. The second question, I just want to get advice on setting up the communication link for auto retrieving of data on the instruments. I know you have a couple of different methods of Modbus, DMP3, and Ethernet. Which one would you advise one to use in all of those three categories? Thanks.
Okay, I just want to first cover the first question. I think we can have a discussion if we want to in another forum where we can just understand how you set those devices up. Because for me, that sounds maybe like a setup issue or something, but just to give you some clarity on it, these devices are all need to be compliant with the standard. That standard is the IEC 61000-4-30, which specifies how a device and when a device should be able to trigger on recording. So all of them is tested for compliance and calibrated to ensure that they accurately trigger on the same point and same recordings. We, for example, have a number of sites, big municipalities with a lot of meters where I can see if there's a network event, all of them pick it up at exactly the same time. So maybe we just need to look at your setup to see if there's not something wrong or advice there, because I won't expect that to be an issue necessarily. On your second question, Modbus TCP is standard on the Vector 3. So DMP3 IEC 61850 is not standard. There's additional modules required to enable that. Modbus TCP is by default enabled. So my recommendation would be to use that if you want to interface. Randolph, I'm not sure if you want to add.
Yeah, just from my experience, they do different things for different people. So, Tiroyane, it really depends on what you want to achieve and what your existing infrastructure is compliant to. So, of course, we would first and foremost recommend you integrating it with Osprey Pro or VECTO Grid OS. Modbus TCP is great functionality for those who want to drive other controllers from the data on it. DMP3 and IEC 61850, or what you might know as Goose, that's a substation protocol or a distributed network protocol, which performs a different functionality than Modbus TCP. Like I said, Modbus TCP is by default on the devices, and the other two, DMP3 and Goose, require additional licenses. So it depends on what you want to achieve with it. We would first and foremost recommend get it communicating to VECTO Grid OS. That's where you will get the highest functionality out of it.
Right. Thank you.
Thank you very much. All right. Any other questions? It's almost 11:30. Brandon, I see your hand. I think after Brandon's question, I'm going to jump over to a demonstration of the VECTO Grid OS platform as well. Yes, Brandon.
With regards to Tiro's question on the relays, I'm not sure for the voltage dips, but we have set up vector 2s, couple of them, and used 3 relay outputs, if I'm not mistaken, 2, 3, and 4, for voltage regulation, unbalance, and THD. Our approach would be, when we usually test them, we would, for say for voltage regulation, we would set a limit of, say, um, plus minus 7% from the declared. So your compatibility upper limit would be 107.5%. And then we would set our limit at maybe say 107%. But how we would test it on site or practically, we would make the upper limit the lower value. We would put the lower limit value on that upper value. So for the upper limit or upper threshold, we would put 93 and not 107. So already when you click apply, then that relay will not close immediately. It will wait for, say, at least 10 minutes, because it will wait for the next 10-minute average value, and then it will compare, okay, that value is now, say, smaller than your threshold, because obviously you have set your threshold now to be 93, and let's say you are measuring 110% constantly, then your threshold is 93%. Already you expect to get an alarm. The same with unbalance. If we are currently measuring like real time, you have a value of say 0.5%. All what we would do is we would set a threshold of maybe 0.3%, just so that it can trigger that, just to test if the alarms go through. So we usually test it without a Omicron, but that's now on the waveforms and not on voltage dips. So
Yeah, I think
that was just my observation.
Yeah, Brandon, that is 100% correct. And I think to add to your conversation, is a good time to jump over quickly to a presentation or to a demonstration of Osprey Pro. And specifically, I want to quickly jump into setting up that monitor that we are talking about right now. So in here, that's the 3-phase voltage dip and swell monitor we were discussing in the presentation, with the exact same window that I copied over. In this specific case, the value was set as 85 and 110, and so on. All right. Now, the value that what Herman is talking about there is actually the 10-minute interval monitors. So I think there just needs to be a clarity on each of these monitors are triggered depending on certain RMS values or certain sampled values. In this case, for the dips, the device is looking at the 1/6 cycle RMS voltage data, and then triggering as soon as one of those samples goes below the threshold. Now, what Herman is speaking about is this voltage unbalance exceedance. This is a 10-minute interval, so it will only trigger exceedance, and then if it's attached to a relay, when the next 10-minute value, so after 10 minutes, that regulation or unbalance or distortion changes or is above the threshold. So if we enable the voltage regulation exceedance limit here, this is something totally different compared to a dip and swell. This is a transient, this is an event, a disturbance. This is standard or stable in stable operating conditions. So if in a 10-minute period, if the average of your voltage regulation is below or above that limit. So you'll need, if you test this and you put this use a relay, you'll need to wait 10 minutes or at least 10 minutes before it's going to pick it up and then close the relay. So I just want to add to that discussion. So that's why important to understand what values are being used to monitor this. For example, the voltage spike and transient monitor is looking at the 50 kilohertz sampled voltage data. So it's looking at basically the instantaneous voltage waveform. So if there's a short spike, it needs to be able to pick it up. So if we use the 10-minute values, or even in some cases the 1/6 cycle RMS voltage, it won't be able to pick up that spike, because this is too quick. It happened a lot quicker than 1/6 cycle. So that's why you then use the 50 kilohertz sample, basically the instantaneous voltage value, to trigger on a voltage spike and transient. So you just need some clarity on that. Okay, so I think to add here, before we get to questions again on the demonstration, you can see the three-phase voltage dip and swell monitor. There's a lot of other that you can set up. Don't confuse the three-phase voltage dip and swell monitor with a single-phase voltage dip and swell monitor. If you've enabled this monitor, it will also trigger for single-phase dips. So this is then unnecessary to enable the single-phase voltage dip and swell if you have the three-phase one on. This is just in cases where you actually have a single-phase connection. Then you don't want to trigger on the second or third phase if there's no voltage on it. You want to trigger on a single-phase voltage. So that's only for that specific case. Then there's other monitors such as significant voltage change, significant current change, current exceedances, voltage spike, transient, digital input output. So if you want to actually connect a state of a circuit breaker, for example, to a digital input, the moment when the state changes of that input, it will trigger a recording. And again, you can set up what data you want to record and for what periods or window. You can also, again, for each one of these monitors, you can add it to a relay to actually operate the relay as well. Okay, so that is the configuration side of setting up voltage dips and swell on VECTO Grid OS or still currently Osprey Pro. Just getting back to voltage dip management, we have a platform that we call the Power Quality platform with the page issues. This was developed for the whole, what we discussed in the presentation, to be able to manage your dip performance and to analyze events. So what we have here is a list of historic events that was triggered on specific points in a network. But very important here is the concept of issues. We are not speaking about a single individual event. We are speaking about an issue or an incident. We call this function incident matching. You'll see that's one of the features of VECTO Grid OS is incident matching. So what it does, because the devices are GPS time synchronized, if you have more than one device installed in your network and more than one device picks up a dip, then all of them will trigger at the same time because 100 nanoseconds GPS synchronization, and the system will automatically group them into one incident because it's the same cause. It happened at the same time, so it's most likely the same thing that caused that event, rather than investigating it per power quality device. So on Osprey Lite, you'll need to individually look at each individual measurement point to analyze it. Here, it's all grouped into one, so you only need to click on one incident to have data of all the recorders that picked up the event. So in this case, there was 3 recorders, all 3 picked up the exact same event. And this is the voltage, current, power, and reactive power spark lines. And then if you click on a specific one of the meter points, you can actually get more information on the right. So this is what I was referring to earlier on one of the questions, that you have your RMS voltage. So here's the dip. It looks like a line-to-line fault that may have happened, causing the 2 phases to dip on red and green. But you can also compare your RMS current on the same page without needing to plot a trend. It's immediately here for you. If you want to view the data on a different measurement point, you just click on it and it shows you the RMS voltage and current for that point as well. But the nice thing of Osprey Pro is the functionality to be able to easily just click on fetch simplified waveforms, and now it plots your voltage and current waveforms as well. So you'll be able to see if there's any spikes maybe in the voltage or in the current, any oscillations that was triggered or anything like that for further analysis, and so on. So this really adds a lot of functionality on here. You have the scatter plot that I was referring to in the beginning, the NRS scatter plot. So you can see all three of them, or this event was seen on 3 places, and all of them is grouped almost on the same place. And it was all Y dips. There's the residual voltage, the duration for each one, and all 3 of them is classifying this actually as an event that was caused or from upstream. So we have built in research papers that is different, where there's different methods to use or to determine if an event was upstream or downstream. And we've incorporated that on Osprey Pro or VECTO Grid OS to easily or quickly determine if the event is upstream. It's still just a method, so it's not 100% accurate, and that's why you need to do your own analysis as well. But from my experience, I've seen it's quite accurate generally to pick up if the event is upstream or downstream. All right, so something that a lot of you that may be familiar with Osprey Pro have not seen yet is there's a button here that you can click on that will actually jump between different international standards, like the SBIMA, ITIC, different standards that determine how certain devices are impacted by this dip. So for example, variable speed drives, it shows a graph to show would my apologies, would a variable speed drive be impacted by this dip or not? And the same for electronics, different electronics. So this is different standards that you can familiarize yourself with to understand if, for example, a motor or a motor contactor or so would have actually operated or be impacted by this event. Okay, it shows you where in the network, so there's a geo mapping, where in the network the event happened, and then very importantly, we have a functionality here to actually annotate this event. And this is where the real voltage dip management comes in, is to now add information to this event. So some of the default information that you can annotate is you can provide a description. So was this for example, a cable fault? You can provide more detailed description where the cable fault happened. Then there's a party responsible, and this is to provide ownership to it. So you can say this event was caused by third party. This is maybe an ESCOM fault or whatever, whoever may be responsible for causing this event. Where in the network it happened, on what voltage level, and then what's the cause? What's the root cause? Is it a wildlife, nature, load shedding, switching? There's a lot of causes that you can set up yourself here in the history to be able to get a performance. So after a year, you'll be able to see the number of events that was caused, for example, by ESCOM. And then immediately you can compare that with the ESCOM dip performance or characteristics. You can go to them and tell them our performance is bad, and these are the number of events that was caused, or these events caused trips. You can provide effects, what's damaged, what equipment was damaged, what's the cost actually of that event. Did it cause your plant to cause downtime? What's the cost implications of that? And all
Maybe
of this
just-
can then be reported on. Yes.
Sorry, Hein, to add on to this is like all systems you implement, garbage in, garbage out. So the better you construct this report or you fill in this detail, the higher likelihood you have of actually getting into further conversations around it. If you keep on flagging things as human errors, you might get a colleague fired, or you might be blaming nature and you haven't done proper investigation. What did cause a dip? So there are further implications into using this incorrectly. But Hein has alluded that a part of a proper power quality management and monitoring program is a responsible person, someone who looks at it that actually does determine what was the cause.
Yes. And then we've developed, based on that information, if you fill in these fields, based on these information, we can then actually provide you more information. So for example, we can give you then a network disturbance summary that will, let's just take, for example, the beginning of June for 30 days, and that will give you tables like this that can help you to understand what's your performance of your network in terms of dips. So you'll know where the events happen, circuit of origin, what's the severity, what sort of event, and if you provide classifications, root causes, you can then see in this month of June, you'll be able to know how many load sheddings were there, how many cable faults, how many overhead lines or bird streamers, or this is how you can then really characterize your dip performance of your network. There's statistical tables like the hour of day, days of the week. If you have it over a year period, maybe you'll see that in the winter or in the summer period, in Gauteng, when there's more lightning, you get a spike in the number of events. And all of these can be exported as graphs, as CSV data, so Excel files. So we try to develop the platform that becomes part of your daily operation or monthly operation, and to use this really as a tool for voltage dip management. And it becomes really powerful when you have more than one device installed that you can use to annotate and to report on. Okay, I think that is just a brief overview of our platform. There's a lot more in terms of this. You can also generate reports. So there's different sort of reports that can be generated specifically now relating to dips. So you can actually generate a voltage event report that will give you a report of all the voltage event that happened on your whole network for all your measurement points. You can generate a specific NRS report. So voltage events power quality assessment. This report will do a report that will plot the events on a scatter plot and provide you with the basic information such as the dip duration, dip depth, and so on. So yeah, I think, Randolph, do you think there's anything I can add here? Let's see if I have an example.
I know that you mentioned it, but that the button top right corner of the scatter plot, that is really useful. If you consider that we have in the past heard back from utilities that they don't really report on type Y dips because they're too shallow. That if you consider that a type Y dip can still knock out a VSD if you just cycle through there to variable speed drives. So if you stop a variable speed drive with a type Y dip, it definitely has an impact on your operations if you are a large manufacturing facility. So it gives you some indication of where NRS 048 does not exactly cater for all users of our equipment. The CBEMA and the ITIC, that's the Computer Builders Equipment Manufacturing Association, they also give you some deeper insight into what kind of further knock-on a dip could have. So your computer tower box might switch off in something that wouldn't affect, say, a manufacturing facility's direct online motor contactors. So it just gives you some deeper insight into further repercussions of dips.
Yes, 100%. So I think this is a good overview of what the system can provide you. As I said earlier, these causes that you can add here, this is just the default. You can add user-defined fields. If there's something specifically that you want to report on, you can actually add more fields here to this, and you can annotate that. And what I forgot to mention is you can now, for a specific incident, actually also report on that incident. So if you fill this in and you click on report, and then incident report, it will then generate a report that will capture all the basic information of the event with all of this that you've provided. So immediately it's something that you can share, send on, bring to your manager or whatever the case may be. So as you can see, it's a powerful tool. Also on Osprey or VECTO Grid OS, when there's an event or an incident, there's notifications that will be sent directly to your phone, so via email, and that is also for you to immediately be able to look at the event even when you're in the field to see what's going on. In that email or notification, there will be a link. When you click on it, it will take you to the specific incident on VECTO Grid OS immediately. So it will basically take you to this page, even if it's on your phone, iPad, tablet, or whatever the case may be.
And just another related topic on voltage dips and disturbance management for the solar EPCs and the facility owners that are considering solar. The question you need to ask yourself is your low voltage ride through and high voltage ride through, what is the current status of those settings on your inverters? And if it is a dip type Y, which is like, I want to say the shallowest kind, you're sitting on 88% of declared, will your inverter keep on generating or will it trip? And then also, how long until it's back up and generating again? So a large inverter manufacturer brand standard setting in a case like that switches the inverter off for 10 minutes. Now, if you are in a part of the network that has a lot of these dips, that can really cause some downtime and loss of revenue for your client. Just something to consider, low voltage ride through and high voltage ride through settings.
Thank you, Randolph. Okay, any questions on the VECTO Grid OS? I don't see any hands at this stage. Yeah, if there's no questions, then from my side, I think we've covered everything. If you think of anything afterwards, you're welcome to send us an email, send myself an email, and I will try and get back to you after that. Thank you again for joining the session. I hope you learned something, or please share it also with your colleagues or friends, and make them aware of the training that's going on in the future as well. Yes, Herman.
Can I ask some questions that's not maybe related, like Osprey Lite from version 4? I cannot install it, and I've tried it on Windows 10 and also on the Windows 7. That's just a normal open. It's not the ESCOM operating system. It's just a normal one that I installed to test it, and I couldn't get it installed, and I was wondering if you've got any idea.
Aaron, can I ask, do we maybe have this conversation just after the session? You can stay online if you want to, and then we can just discuss that. I just don't want to keep anyone else up. So if you want to go, thank you for joining. I'm not sure, Tebogo, is there anything from your side you want to quickly add before we end the session?
Yes, please, just 5 seconds. Thank you guys for attending the training. We will be sending the training video to all of you, but there's 5 people that I don't have their email addresses. Can you please, I'm going to mention the names, and can you please just write your email addresses in the comment section. It's Carol, it's Florence Malele, it's Leslie N, Tabiseng Kupa, and Sylvia Moratsetla. Can you please just write your email addresses in the comment section so that we can include you in our email when we send out the video. Thank you, and yeah, goodbye for those that are leaving. And yeah, thank you, Hein.
Thank you, Tebogo. Then from my side, thank you all for joining. We will share the presentation. We will share the video as well. I think it will also be uploaded on YouTube, so you'll be able to find it on there. I'm gonna end the recording then, so that the other questions that's not relating to this topic can be asked after that. So if you want to leave, you're more than welcome to leave at this point. Let's give it a minute and then we'll take other questions. Thank you.
Yeah, thank you very much. Most interesting. Thanks. Bye-bye.
Thanks, Lawrence. Bye-bye.
Thank you. Goodbye.